This is Math 432, Applied Combinatorics. I'm Professor Asaf, and today I'm going to introduce a rather bizarre definition of colorability of a family of subsets. So here's the definition. Suppose you have a family F of subsets of the numbers 1 up to n of size d. Let's do an example as we go through this definition. So here I have the numbers 1 up to 5. So for my example, I'm going to let n equal 5. And I'm going to take d to be something nice and simple, which will just be 2 for this case. Okay? So I'm looking at 2 element subsets of the numbers 1 up to 5. Okay? And I'm looking at a family of those, so I can take a collection of them. So what would an example be? An example would be I could take the numbers 1 and 3, and I could take the numbers 2 and 4, and I could take the numbers 1 and 5, and then I could take maybe 2 and 5. And this would be my collection F. So this is one example of a collection F of subsets of the numbers 1 to 5, each of size 2. Okay? We say that this set is 2 colorable if there's a way to choose for every eye, either choose red or blue, such that in every one of these sets, I have a red and a blue. Okay, let's see if we can do that. For this set, is this set 2 colorable? Okay, so we have to think 1, 3. I need one of these numbers to be red and the other blue. Well, let's say, okay, that means I'm going to color the number 1 red and I'll color the number 3 blue. That means that I've definitely got the 1 is now red. The 1 is everywhere it appears in my family F. And the 3 is blue everywhere it appears in the family F. Okay, and now I have my next set, 2, 4. Well, I could take 2 to be blue, and I could take the number 4 to be red. That's something I could try. So here's the number 4 is red, everywhere 4 appears, and the number 2 is going to be blue everywhere that 2 appears. And now I say, okay, well, what about the number 5? Well, here I see that 5 has to be blue, and here I see that 5 has to be red. So it looks like I can't do it, right? If I make 5 red, this violates the condition, and if I make 5 blue, this violates the condition. But I made a choice here with 2 and 4. I didn't have to make that choice. That choice wasn't forced on me. So maybe a smarter way to do it is before I make the choice of 2 and 4, after I've made the choice of 1 and 3, just back up and say, okay, 1 and 3 I've chosen like this. Now the next number I should pick is 5. I know that 5 can't be red. 5 has to be blue. So let me just choose 5. Okay, I've chosen 5 is going to be blue. Now, what do? Well, now I still have a choice of 2. 2 would be the next thing that I would choose. Not 4, because there's no constraint here, but 4 I know has got to be red. 4 definitely has to be red so that I get those patterns. So, okay, I've chosen a red. And now I need to choose the number 4. And I can see that if I take the number 4 to be the blue one, then this way of coloring my set, red, red, blue, 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 okay, this color the numbers 1 up to n makes this family 2 colorable. So then I would say this family is definitely 2 colorable. Let's do another example. Suppose I took the numbers 1, 3, and then I'm going to take 2, 4, and then I'm going to take 1, 5, so the same up to there, but then I'm going to take 3, 5. Let's see how this set fares. Now again, this was the coloring that I chose to make this guy work. So let me reset that. It doesn't have to be that way for the next one, but let's go through the same process that worked. First, we'll take the number 1 and the number 3. So 1 is going to be red wherever it appears. And now, what about the number 3? Because these have to be different, 3 is going to be blue wherever 3 appears. Even though I've made a choice of red and blue, up to switching red with blue, this was unique. This was forced. These have to be different. And now I can already see that I'm in trouble with the number 5, because the number 5 shows up both with 1 and with 3. This is related to the Ramsey theorem idea because I can see that 1 and 3 are different, 1 and 5 are different, and 3 and 5 are different. So 1, 3, and 5 form a clique. There is no way that I can resolve this. There's no choice of a color for 5 that lets this work. So this family is not 2 colorable. Okay? that's the definition of what it means to be two colorable. Hopefully that's given you a little bit of intuition. And now let's test that intuition with a problem, or rather an example. Suppose that I let n be 2d minus 1. Let's do an example. So if I let maybe pick d to equal 3, then my n that I would be picking would be 6 minus 1 equals 5. Okay? And suppose that my family F that I take is all 3-element subsets of the numbers 1 up to 5. Okay? I want to prove that F is or isn't too colorable. This is sort of specific, but in this I've made it nice and specific. So here F is all 5 choose 3, which is 10 3-element subsets of the numbers 1, 2, 3, 4, and 5. Is this family too colorable? Is this family too colorable is the question. Well, I've got these 5 numbers here, and what I need is that every collection of 3 of them, I definitely get 2 that are the same, or that are different colors. So no, why not? So F is not too colorable. Why not? Well, I'm coloring these 5 numbers, either red or blue, okay? So we must have at least 3 numbers that are the same color by the generalized pigeonhole principle. If I'm coloring them 2 ways, at least half of them. And now we can see that actually that's going to work out in general here too. 2D minus 1. The pigeonhole principle is going to say at least D of these numbers from 1 up to n are the same color, which means that when I take all D element subsets, I'm going to have one subset that's all the same color. It's either all red or all blue, which violates the notion of being too colorable. So this is a great application of pigeonhole principle. It comes up whenever there's a Ramsey style problem, which this is. In the next video, we're going to find another example and another theorem that we can prove using a new method in combinatorics that's a really amazing method for proving that something is doable, which is the probabilistic method.